more triglycerides, the other more cholesterol esters. We have tested this a little bit in yeast and we don't see a difference. And then also you have some lipid droplets, for example, that are in close contact with peroxisomes or like more in contact with like reticulous. And there seems to be like transpiration, but this is not very well understood, but it's very studied a lot. All right, so thank you very much. Again.
I want to thank the organizer of this meeting for having invited me and for what is turning out to be a very interesting meeting where the discussions are quite broad and I'm quite fascinated by being able to cover different topics. So I have always been interested in looking at things. I have to tell you that I don't see in 3 dimensions. My world is 2 dimensional, so I always had this thing that I want to see things in 3D. So I started to do... Not yet. I started to do crystallography, cryo-EM, and now we're doing lifestyle imaging. And so what I want to do today is I want to show you 2 problems that we're addressing. One is very mechanistic. Inside the cells, I'll show you how we can use fancy microscopy to track teeny objects and how they change composition. So this will be focused on lipids. So that will be like the first part. And then I'm going to switch totally gears to a different level of organization. I'm going to go to the ability now that we have to image things in 3 dimensions, close to single molecule sensitivity with very, very high resolution. Now this is a revolution. For me, has changed completely my lifestyle. I must confess I have some problems sleeping. And the person that is responsible for doing that is years ago, and you might recognize he was one of the people that got recognition with the Nobel Prize for single molecule super resolution imaging. And so when he was getting that recognition, already was developing another form of microscopy. It's an acronym which is very long. It's a lattice light sheet microscope. The details don't matter too much right now. But it's a way in which you can see non-invasively inside cells with exquisite detail. So everything was fine. We built an instrument. We got it in the lab, and we've been doing this for several years. And then suddenly he came with another idea, which I'll show you, which is to bring the technology that the astronomers use to sharpen the images when they use the telescope. When you do that, now it turns out that you can go into animals, for example, organelles, you will see also from David's talk later, and you can go now into the multicellular space and look at what's going on inside cells. So I think what I wanted to convey sort of a philosophical level is that at least I'm switching from a mode where I was doing hypothesis testing. For those of us that are in the United States, that's what NIH always wants. What's your hypothesis, right? The papers also, the journals tend to also ask you, what's your model, what's your hypothesis? To another mode, which I'm calling hypothesis driving. So it's like Renaissance to me. We just look, describe, and then let our brains go. So I'm going to give you these 2 stories. One of them, I need to turn off the light, sorry. Okay, so one of them has to do with the issue of phosphoinositides. So these are specialized lipids that we have inside the cell. They have charge, and they tend to be platforms on which proteins come and they signal things. So I'm going to show you an experiment that was done in my lab by Kang Min Hei, a postdoc in the lab, with help from Bobby Marsland. He was a PhD student, so he did the theoretical part, which I won't have a chance to present today. I'm sorry for that. And so this has to do with these lipid conversions going on inside the cell. So I'm going to focus on the endocytic machinery. I should add that through my career, I've always been interested in how cells eat and how cells spit. So when cells eat, there are many ways they do that, and the one I like is what we call the clathrin-mediated route of entry. I'll come back to that in a minute. So I'm going to show you that he developed a special type of lipid sensors that with exquisite sensitivity can detect the lipid composition inside cells. And then the second part will be this problem of how you can now image in multicellular context with very high sensitivity. So this is a work that has been driven by 2 people. In Eric's lab is by Tsung Lee, who developed this adaptive optics, as we call it, lattice light sheet microscope. And Gokul is a fellow in my lab who is driving, spearheading all the efforts that we're doing, both in terms of image analysis, building the systems, etc. Okay, so I'm going to then start with dynamics of phosphoinositide conversion, then I'll go to the imaging in tissues. I would like to point out that this we can do with very high temporal resolution. We can go to 20 milliseconds per plane, per plane of imaging. We can even do faster than that. In some cases, we can do a few milliseconds. And the precision of our measurements can be about 30 nanometers. So that's the location where objects are. Of course, the resolution is not as high. It's more in the 300 to 400 nanometers range. So let me start with this. This is what I call a molecular animation. Another movie. It describes how clustering works. To summarize the studies from a number of groups including us, where we went through the crystal structures, binding constants, cloning, etc. And we depicted here how this machinery is forming, and it's what we understand at some level of certainty. Right? So the time this movie is running is what it takes as self-image. It's called a clustering forming, which is the state of the art. Remember in the budget meeting, maybe there are hundreds of proteins that are coming into place, a lot of very weak interactions, all at the high micromolar level. But then there's the neck from the vesicle. This is the protein dynamic, that's the source of energy. The next switch, breaking the neck, which is working to do the tightening of the neck, nutrition. Then the last part of the reaction is how you regulate the dynamic of the that is done with enzymes, which is also energy sensitivity, which is gravity, and there's a cofactor that brings those things up inside the reaction. So you will see in a minute why I'm pointing this out. But what you see here is all the results from our cryo-EM crystal structures. Okay, so what you saw here is about 30 45 to 50 seconds in average. We have hundreds of these guys doing this in every cell. So every eukaryotic cell has it, and we have a similar process that goes from yeast to normal. You'll hear more from I think, from David later on. Okay, now there's a puzzle here, right? What happens is that this machinery that was encoding this does it only after this structure has pinched off from the membrane. So even though the components can recognize the code components, they are not recruited. They're not recruited to the lattice that it's forming. Right? It's only after they pinch that this gets recruited. That's a puzzle. What's the signal for this? So it turns out that the signal is lipids. So I'm going to show you that when you are making a coded bit, so it's this code that is forming here and is deforming, and that's the dynamic in this location, and then you pinch, and then the encoding machinery comes and destroys. There's this enzyme, which is the 70, which is being recruited, and the encoding, and this oxalin, which is the cofactor. So it turns out that this cofactor, which is structurally depicted here in the bottom, has in the C terminus, what we call it the J domain, which is going to recognize the GC70 as a binding site for clathrin, and then at the middle terminus has this thing that we call the PTEN-like domain. PTEN is a fold that is a tumor suppressor, and it's a phosphoinositide enzyme. It's actually removing phosphoinositides. Now here, this has sequence similarity. The structure is quite similar to the PTEN, but the catalytic pocket doesn't exist, has been mutated. So what I'm going to show you is that this portion here actually binds lipids. It likes to recognize certain classes of phosphoinositides. I'm going to show you that it's what is being recognized is PI3P and PI4P. It also recognizes 3,4-P2. It's a special head group phosphorylation we get. The plasma membrane is very rich in 4,5-P2, and I'm going to try to show you how we think it happens that we can make the conversion of lipid, that we have the 4,5-P2 here into getting the 3 and the 4 later on as we pinch. So this is the biology. So what we have here is a cell that has been placed in the microscope, and we're looking at the bottom surface of the cell. So what is in red is the clathrin, which was this triskelion that has a fluorophore in red, and each one of those spots corresponds to each one of those structures that are forming in the bottom of the cell. Later I'm going to show you an image throughout the cell as well. The image to the right is this oxalin. We added GFP, and you can see that it's blinking. So it turns out that those blinks are happening at the end of the code when it's falling apart. So for example, here you have fluorescence intensity, and I've just clustered a number of these traces by cohorts. So just focus, let's say, in the very last one, which I'm going to trace with my pen. So the fluorescence intensity in red, which is the clathrin, is going up all the way to the end. So this is the assembly process, and then it catastrophically comes down. And that coincides with bringing up this cofactor oxalin as a pulse. This happens after the vesicle has pinched. Okay? So that's all the biology of the process. Okay, so what we have found on taking this protein and following how it gets recruited, and then with a trick I'm going to show you in a minute where we can replace with the natural PTEN with other domains of other proteins known to bind specifically to lipids. What's going on is that the plasma membrane has PI4P2, which is sort of depicted here. Okay, there's also a little PI4P trace amounts, but then when we pinch, which is at this point here, there's a pulse of PI4P while we're consuming 4,5-P2. We have a pulse also of PI3P, and then PI3,4 appears and stays and then goes away. Now, for those of you that know the endocytic pathway, this vesicle here, after it encodes, is going to traffic to the endosomal compartment. Unfortunately, I won't have time to show you now, but we have done the same class of experiments as I show you with this oxalin following RAP5, and it turns out that RAP5 is only recruited after you encode it, and it's actually part of recognition of this 3,4. Okay, so I'm going to show you that not only you get these waves of lipids, but these are also the platforms on which things come in. So oxalin likes PI4 and PI3, and that's the signal that brings the encoding machinery. When it encodes, then we're going to get a wave of 3,4, and that is what's bringing the RAP5. I'll show you also that we have the enzymes that are responsible for modifying these lipids. So I won't have time to go through the whole map, but we have done simulated all this. So we have all the results and the timings and changing and putting mutations, etc. And then what we have done with Bobby is put all the binding constants, all the rates of all the enzymes, and it turns out that not only you can model the process, you can also do predictions in the system, which I think solidifies what we have. Okay, so then the idea is that we have our clathrin code. This is actually this is one of the first. I think this was the largest cryo-EM, the largest structure solved by cryo-EM. It was done about I think it's now 14 years ago. This structure is 22 megadaltons. At the time, it took us about 3 weeks of CPU time to solve the structure. Today you can do it in a few hours, just full of your content. This model here, in blue is the clathrin, in red is the component of oxalin that is binding to the code, and in green is the HSC70. And the resolution we have here is a combination, roughly somewhere between 8 and 10 angstroms. Okay, so the idea for our sensor is that we can replace now the PTEN domain with any lipid binding domain that we can get all from the literature, that people know their specificities. We put the EGF here at the middle terminus, and this guy is recruited exactly like the natural protein. It will give you a spike if we get the correct lipid binder, or it won't recruit, etc. Right? I should add that these changes don't interfere with the biology, so the endocytic machinery is fine. And the movie I'm showing you is all single molecule sensitivity, so we don't need to overflow or overload the system anymore. So these are examples of some of the domains that we have replaced. I think the PTEN-like, for which we saw the crystal structure a few years ago, and we have other domains from the literature that we took, PH domain, PX, ENPH, etc., with known lipid binding specifically. So just simply use swap, and then you end up having this sort of coincidence detector where it gets recruited now in different fashions. So these are now chromographs, so we're just looking at the bottom traces. So this is time in this axis, and then we have the signal for clathrin in red, and in green would be this oxalin, the replacement. So these are the spikes that we have. We put PI3P, the same with PI4P, and with PI4P you get a spike that then lives longer. If I were giving you the signal for PI4,5P2, the signal will have come together with the red and then disappears. So that's the consumption. Okay. So the summary of this result that we have is that we have a process where we get the signal of the PI452 until we pinch, and then it gets consumed. And then again we get a spike on PI4P, the same for 3, and the 3,4P2 goes up and then decays much slower. So I won't be able today to go through every single experiment we have done to figure out which enzymes were doing that. So I've just listed them here in the next part here. So there's a protein, for example, called synaptogenic. Synaptogenic binds to the clathrin coat, right? This is work that was done in Pietro Vitamini's lab primarily. So synaptogenic is recruited the moment you have a clathrin coat, it comes on plate. Synaptogenic is consuming the 4,5,2, it's a 4,5,2 kinase. But then what happens is that even though you have the enzyme here and you're consuming the substrate, it's exchanging with the adjacent lipids. So they're diffusing very fast within milliseconds, right? So even though the enzyme is consuming, you replace very quickly. Okay? And the same is true for some of the other enzymes that we have here. There's another one here called OCRL, another enzyme that also the Canili has been working, also a region in Italy. So this is also a 4,5,P2 kinase. It's also recruited to the clathrin coat, but it's recruited actually at this stage, a little bit later, when the coat is already falling apart. So those two are required to consume the 4,5,P2. If you get rid of one or the other, nothing happens. You have to get rid of both. Even worse, if you get rid of one of them, the other enzyme shoots up in concentration. For those of you that think about signaling inside the cells, I found that extremely fascinating and weird at the same time, because the regulation of the OCRL or the synaptogenic, depending on which order you do the experiment, is at the transcriptional level. Right? So somehow it's sensing lipid composition in the coded bits, and that somehow gets transferred all the way to transcription to regular. I must confess I have no idea how that works. Right? So I have a few other enzymes, and it really doesn't matter. I won't go into that detail right now, but we have other enzymes that are also modulating lipids. And here at the bottom, I just mentioned two oxalins. There's one called oxalin 1, and the other one is oxalin 2. So oxalin 1 is the prevalent form of this cofactor in the brain, although we have it in other tissues as well. And oxalin 2 is present in basically every tissue in your body. So what we found is that oxalin 1 likes to recognize PI3P, and oxalin 1 works in the plasma membrane. Oxalin 2 recognizes preferentially PI4P and also PI4P. So that also, and also 3,4P2. It also goes to the plasma membrane, so that part is good. But then when you look in 3D, where else do you have this oxalin working? It turns out that there are coded vesicles in the secretory pathway, and those vesicles contain PI4P. They don't contain PI3P. So sure enough, this oxalin 2 goes to those coded vesicles that are inside the cell. So the signal that is sending the enzyme to the right place is dependent on the lipid composition of the vesicles. And finally, I also mentioned that RAB5 is being recruited to the coat after you encode it, and that requires having this the PI3,4P2 lipid. So there's also a protein that engages and then brings it in, and the gap actually required for the RAB. So with this, what I'm trying to point out is that we have a system which is very complex. Things are happening very, very fast. It's all in a matter of seconds. There's vast amount of traffic. There are all these signals going in. All the interactions here are all in the micromolar level. So if you go with one protein at a time, given the cytosolic concentration, nothing should work. And it's working, I think, because you tend to have, usually in this protein, there are two binding sites. There's one for clathrin, one for a lipid. Each one is micromolar, and you end up having this coincidence in detectors. Okay, and so this is just a summary of the lipid situation that we have. So the plasma membrane, I just pointed out, we have the 4,5P2 and 4P. The endosomes like to have PI3P, and then in this multivesicular bodies, which are sort of deeper forms of endosomal structures, all these lipids depicted here, and also in the secretory pathway, as I just pointed out, we have PI4P. And so what we found is that there's this transient modifications that happen along the coded vesicles. So imagine this is the coded bit, and you're making the coded vesicles. So I'm just highlighting here the various switches that we're having in lipids and the RABs that are being recruited. So I think that something similar can happen somewhere else in the cell. We haven't studied this in detail, but I imagine that the same would happen, or something similar could happen in the secretory pathway, where you're also having lots of signals and sort of diverted traffic going on. Okay, so I now want to change gears to the second part of the talk, which is imaging things inside the cell. So there's an expansion of this, but what I'm going to now change is the way I'm going to present you the data. So I won't show you enzymes anymore, and there are going to be lots of movies. You will see some movies where we can follow the endocytic system.
With or without music?
I'll show you that you can follow, for example, the endocytic traffic, not only at the level of a single cell, but also multicellular organisms. And I'll also show you other type of biologies that, as I said, at least for me, is keeping me awake. Okay, so we're used to use microscopes where we have an objective. You shoot a beam throughout the cell, and the beam is like the pointer, so basically a Gaussian-shaped beam. It illuminates the whole cell, and then what we're doing is imaging in a focal plane, right? So that's how a standard microscope, whether it's wide field or a confocal scope, is operating. There's another way of imaging, and it started with experiment some years ago, which involved using sheets of light. So you can have still a Gaussian sheet coming from an objective, and it's coming, and you can through an angle through the sample, and then you can sweep the beam, and then orthogonal to the plane that you're forming, you can image with a second objective. So this form of imaging is light sheet microscopy. It's very powerful to look at the organization of cells in, for example, developing embryos. The problem of this, however, is that this beam here is quite wide, can be several microns in diameter, so it kills your ability to have high resolution, and also similar to the standard form of microscopy, because this beam is basically illuminating the whole cell, you end up getting lots of bleaching, and it's very invasive to the cells. So Eric Betzig then invented another way of doing the microscopy, where he can have a beam that becomes much thinner, and that's an instrument that he calls a lattice light sheet microscope. The trick is very simple. So under normal conditions, you will have an objective, and if you illuminate the back aperture of an objective, you get your Gaussian beam, you're basically getting a full transfer of the beam. If you illuminate with a ring, what you get is a vessel coming out, a vessel function. So that's a very complicated beam with lots of arches. Now you create a lattice, an array of those beams, and you can organize them so that they're all coplanar. It's still a very complicated beam structure. But if you bring all those beams together, since you're using a laser to do this illumination, you get interference. And there's a sweet spot where everything becomes very tight, and you effectively get now this sheet of light. You still have to veer a little bit the beam with a galvo mirror very fast, but you end up having now a beam where this thickness here is about 400 microns, 400 nanometers in thickness, right? And so that's close to doing TIRF microscopy, total internal reflection microscopy, but in 3D, because now we have this objective that is looking orthogonal. Okay, so that's how the instrument works. So basically you have the lattice, you dither, and then if you have a cell that is expressing fluorescent markers, in this case, a marker just at the cell surface, you can just move the sample against it.
Optical reduction, yeah?
Excuse me? It's always, yeah. So, although we can do better than that. I mean, if you're interested, we can discuss that later. We can structure also the light to go break the barrier of diffraction limit. So you can scan your sample against the beam, and you can do that either by moving the sample with respect to the beam, or you can move the beam and the objective and have a stationary sample. Because it does really, that doesn't matter. But you can collect data, and the fastest we have done is about 3-5 milliseconds per plane. Normally we do 20 milliseconds per plane, and that's so that we don't bleach too fast our fluorophores, usually GFP or similar molecules, right? And then the amount of light that you're putting in the cells is low enough that is not damaging, and you get, for example, cell division, things like this. It's very hard to do an experiment when a cell divides using a normal microscope, because you immediately get DNA damage and the cell cells freeze. All this is gone now with this form of microscopy. So all this was done in Eric's lab. Okay, so I just brought one example just to give you a little bit of context. So this is now from our lab. This is a cell, and we have a surface marker in the cell. And this particular cell has these spikes that you see here. So these are Filipodia. I must say that before this movie, I always have seen the Filipodia, these projections, sort of parallel to the glass. So with the normal microscopes, it's very hard to see these guys sticking out. And with this now form of microscopy, now you now get a good sense of the 3D. So this particular movie was taking such that we're taking a spacing of 3 microns per plane. There are 150 planes on each stack. And for this particular experiment, it took us 3 seconds to collect the stack. There are 15,000 images, and this is a 7-minute movie. No bleaching. That we pick up. No clue. Is that good? I should know. I don't know. It doesn't really matter. Who cares?
Well, I just want to...
No, the reason we were looking at this is because Emma, when I was looking at the experiment, he was interested in exosomes. So he chose a cell that was making exosomes. I just don't remember the name. Okay? And this protein here is supposedly enriched in endosomes CD9. It's a tetraspanin molecule, it's a transmembrane protein. Well, it turns out that that's how we found that it was full of Filipodia. And we were not expecting that. It was just an accident. Okay, so this is another cell. In this case, this is a cell that's been gene edited with this protein called AP2. That's the protein that links clathrin to the receptors. Okay, and so this has been gene edited. This follows principles that David brought in some years ago to convince the community that we should be using gene editing instead of transfections to then follow fluorescent proteins. The idea that you can express this at endogenous levels. Right? So this cell is expressing this, and this AP2. So each spot is one of those clathrin codes, and this happens to be 50 planes, I think, every 2 seconds. Now the reason I'm showing this movie is because this is a cell that we just dropped on glass, and you can see that this cell dropped, and now it's spreading out, right? And so what you see here is a volumetric imaging of the whole cell. And you see that there's material that is sort of flowing backwards, right? This is the dorsal surface of the cell. So it's a bit counterintuitive, but it's depicted here. You have the cell that is sort of expanding, so it's a lamellipodia and lamella. So the membrane is expanding to the left, and then we have a backflow. It's a centripetal flow that we're having in the top, right? So that's counterintuitive. We can discuss later the science of this, but this ended up being the motivation for this poster thing that we have for this.
Now Mark
actually made this.
This is actually a mistake.
So here what is encoded is time in colors, right? So what is blue is things that are quite old in the image, and these are different frames, each frame with different colors, and you see the fresh guys are from outside and going in. So that's the poster. Yes, Mark? Thank you. Okay, so let me compare you now the spinning disk with a lattice light chain microscope. Some of us use spinning disk. I was very proud of the spinning disk because I think we got the 3rd spinning disk in the United States. I think that was in '99. So we used it heavily, and I thought it was a cool instrument until I'm going to show you the movie what happened. And now I put my spinning disk in eBay. So this is again the gene edited cell. It's going to be for AP2, and I'm going to show you what happens when you collect these 50 planes as a function of time. So we're taking stacks, right, as a function of time. And the cell in the bottom is a similar cell. These are stem cells, actually. This is a form of cancer cells. And the bottom will be the same thing. And the way we organize the experiment is that the amount of light that is coming to the 2 cells is equivalent, so that we can get the same signal to noise. Okay? So you're going to see the 2 movies running together. And here in the right, you're going to see the a plot of the signal to noise for the top and the bottom. So this is what happens. So you see after 20 stacks, we don't see anything with the spinning disk. And the other one, we went, I think, 100 of those stacks. Maybe we lost 10% of the signal, and we stopped because we got bored. So the point here is that this form of microscopy is very non-invasive and allows you to now do volumetric imaging. And you can then extract information. You can get positions. You can get amount of signal. You can get composition. You can get rates. You can get kinetics. So an example is shown here. So in this case, we're now tracking every single clathrin code here. And the traces that you see here correspond to, in this case, we're just following the position of the clathrin codes, right? So it's color-coded on time. But we can also follow content. So I won't have a chance to show you, but we can now put cargo. We can put the preferred cargo for these clathrin codes could be transferrin or LDLs or viruses. And we can now track for every single endocytic event how many molecules are being captured, how fast being recruited, and what's happening, right? And then we can, of course, do this with several molecules at the same time. So in the lab, we have now, I think, gene-edited at least 30, 40 lines, different genes for the endocytic traffic, and trying to get correlations and times to understand what's going on. Okay, okay? And those details in the right really doesn't matter for now. Okay, so we've done lots of studies with cells in glass, and that's okay. And I was very excited. In fact, we had one machine in the lab that we had built together with Eric, and then we had to transport it to my lab. Nobody wanted to get the insurance. It was like $250,000 or something like that instrument, and I wanted to move it from Geneva Research Campus in Virginia to our lab. And I said, okay, it's easy, right? I'll just hire a piano moving company, and they're used to move expensive pianos. They refused to do that. I tried FedEx. I said, well, as long as you have an invoice and it shows exactly what it is, well, no way I could do that except the cameras and the objectives, right? So we sent that by FedEx. The rest we put it in an SUV, and we drove it for 12 hours.